In this video, we're going to talk about op amps. An op amp is short for an operational amplifier. Op amps are basically high-gain differential amplifiers. These devices, they amplify the difference between the input voltages V1 and V2. Now, the op amp has a very high input impedance, but a very low output impedance. The negative terminal here is known as the inverted input. So if you apply a signal to the inverted input, the output signal will be 180 degrees out of phase with that. The positive terminal is the non-inverted input. So if you apply a signal there, the output signal will be in phase with the input signal at V2. So here's the basic layout for the 741 operational amplifier. Pin 2 represents the inverted input, and pin 3 represents the non-inverted input. 6 is the output pin. Pins 4 and 7 is used for the power supply. That's where you'll be connecting the batteries to this op amp. Number 8 is unused, and 1 and 5 is the offset null pins. Even if there's no signal applied at the input, the operational amplifier can still generate an output voltage, and this is known as the output offset voltage. And so you could use these pins to set the output offset voltage to 0. But that's another topic for discussion. So here is a basic circuit diagram of an inverting amplifier. The signal is applied to the inverting input, which is represented by pin 2, and so the output will have the inverted signal. RF is known as the feedback resistor. This resistor takes some of the output signal and feeds it back to the input. So as a result, it reduces the voltage gain. Now, when you have a feedback resistor, the voltage gain is said to be a closed loop voltage gain. And that gain is equal to RF divided by Rn, or the input resistance. Now, of course, because the signal has been inverted, we need to put a negative sign here. So that's how you can calculate the gain for this particular circuit. Now, R should be set equal to the parallel combination of these two resistors. So R is going to be the product of the input resistance times the feedback resistor divided by the sum of those two resistors. Now, what happens if we get rid of the feedback resistor? And let's get rid of R as well. In this case, the op amp will no longer be in closed loop mode, but rather it's going to be in the open loop mode. So the gain will no longer be called the closed loop voltage gain. Instead, it's going to be called the open loop voltage gain. And so that equation won't apply if we don't have a feedback resistor. Now, the typical open loop voltage gain, represented by G sub V, could be as high as 200,000. Now, the output voltage will be limited based on the supply voltages at pins 4 and 7. So keep that in mind. Now, let's talk about how we can connect a battery or a series of batteries to the op amp. So this is how you want to connect the supply voltages. So let's say if we have two 9-volt batteries. So here's the positive terminal of one of the batteries. Here's the negative terminal of the other one. The ground will be at the middle between those two batteries. And this will be connected to basically pin 7 of the op amp. And this part will be connected to pin 4 of the op amp. So let's put this all together. So here is the 741 op amp with its two input voltages. Here is pin 7 and this is pin 4. And here's pin 6, the output pin. And here we're going to put the batteries. So this is negative V, and over here this is positive V. So this is V out, this is V1, V2, and then we also need to connect the ground to it. But let's add some resistors to this circuit. Let's turn this into an inverting op amp. So this is the input resistance. Now we do need our feedback resistor. This is going to be R, and we need to connect this to the ground. And the ground connection is here as well. So if you want to, you can just draw a line that connects those two parts of the circuit. So that's how you can connect the 741 op amp to a series of batteries. So you need basically two batteries. So this is 9 volts each. It could be more, but in the middle, that's where you're going to put the ground. Now let's go over the next type of circuit, which is the non-inverting amplifier circuit. So we're going to use the 741 op amp one more time. So this will be the positive terminal and this will be the negative terminal. So notice that I flipped it. Now we're going to apply the input signal to the positive terminal. So because it's a non-inverting amplifier, the output signal will be in the same phase as the input signal. It's not going to be inverted. Now we're going to have a resistor between pin 2, that is the inverted input, and the ground. So let's call that the input resistance. And we're still going to have our feedback resistor between inputs 2 and 6. So notice that if you compare this circuit with the inverting amplifier circuit, the feedback resistor was still between pins 6 and 2. So that hasn't changed. Now let's not forget to put the supply voltages. So positive V and negative V for pins 4 and 7. Now, the closed loop voltage gain for this particular non-inverting amplifier is going to be, it's still the feedback resistor divided by the input resistance, but with an addition of 1. So it's the same gain as the inverting amplifier, but adding 1 to it as well. So that's how you can calculate the gain for this particular circuit. Now, there's another term that you need to be familiar with when dealing with op amps, and it's something called slew rate. The transistors inside the integrated circuit of an op amp has limited switching capabilities. At high frequencies, they may not be able to switch on and off as quickly based on how fast the signal is alternating from its positive to negative cycles. So this value becomes very important when calculating the maximum operating frequency of a particular op amp. It's the slew rate divided by 2 pi times the peak voltage. This is the peak output voltage of the signal at pin 6. Now, a typical slew rate value would be like 0.5 volts per microsecond. So that's 0.5 divided by 1 times 10 to the minus 6 seconds. So that will correspond to a frequency of 500 kilohertz. What you need to understand is this. As the frequency of the input signal increases, the gain of the op amp decreases. and so certain op amps don't work at very high frequencies. Some are designed to handle higher frequencies, but others just don't work well at high frequencies, so keep that in mind. Let's work on an example problem. So here we have an operational amplifier circuit, and we're given the voltage of the input signal, and we want to calculate two things. What is the closed loop voltage gain of this particular circuit, and also what is the output voltage? Let's focus on the gain. Now we need to know what type of amplifier we have. Is it an inverting amplifier or a non-inverting amplifier? Now we can see that the signal is applied to the negative inverting input of the op amp. So it's an inverting amplifier, which means that the gain is negative RF over the input resistance. Now the feedback resistor is 40 kiloohms. The input resistance is 2 kiloohms. So negative 40 divided by 2, the closed loop voltage gain is negative 20. Now keep in mind, a negative sign simply tells us that the polarity has been reversed, or that the output signal is 180 degrees out of phase with the input signal. Now what is the output voltage? If the gain is 20, it's going to be 20 times more than 10 millivolts. So it's 10 millivolts times 20. 10 times 2 is 20, so 10 times 20 is 200. So thus, the output signal will have a voltage that will vary between positive and negative 200 millivolts.